So with this one, we're just going to go through some practice problems related to the colligative properties. So the first one here, glycerin, is a non-volatile, non-electrolyte with a density of 1.26 grams per milliliter at 25 degrees C. We want to determine what the vapor pressure of a solution is going to be if we take 50 milliliters, of glycerin in 500 milliliters of water. And with it, we know the vapor pressure of pure water at that temperature is going to be 23.8. So with it, just remember, as we have a non-volatile solute, it's essentially going to keep more of that solution in the liquid phase. So we're going to see the vapor pressure is going to decrease. But for this one, we've got to do a couple different things. We've got to figure out the mole fraction. But since we're focused on the vapor pressure of water, we've got to figure out the mole fraction for the solvent in this case. So it's going to be a little different than normal. And with this one, it's not included in the question, but we're going to also know that the density of water at this temperature is just going to be 1 gram per milliliter. So since we have 500 milliliters of water, we're going to have 500 grams of water. But we'll have to use the density of glycerin in order to figure out how many grams of that substance we have, so we can figure out how many moles of this substance we have. But I'm going to do the work on this slide, so we've got a little bit more room to work with. But ultimately, we're going to be using the Raoult's law equation. So the pure vapor pressure on the right times the mole fraction for that solvent is going to give us the vapor pressure of this solution. And then, like I said, since we have 500 milliliters of water, that'll just be 500 grams. And then since the molar mass of water is 18.02 grams per mole, that means we will have 27.75 moles H2O. And then for the glycerin, we had 50 milliliters of that. And then we had a density of 1.26 grams. So we can take that volume, multiply it by the density to get the mass, and then we can use the molar mass. So since we had the formula on the previous slide, we can figure out the molar mass of glycerin is going to be 92.09 grams per mole. So we can determine that we're going to have 0.684 moles of the glycerin. And now that we have both of those pieces, we can get the mole fraction, and then we can ultimately just put it back into the equation there. But again, we're looking at the mole fraction of water. So in this case, we're going to have the 27.75 on top, and then on the bottom, we'll have the sum of those two. So we'll have 0.684 plus the 27.75, because we want to make sure we're accounting for all of the moles in the solution, not just the solvent or just the solute. We want to make sure we're accounting for everything. So in that case, we're going to have 28.434. And this gives us a mole fraction of 0.976. And that makes sense. So again, remember, mole fraction has to be between 0 and 1. And then since the vast majority of the solution is going to be that water, it makes sense that this value is pretty close to 1. But then for the vapor pressure, we'll take that mole fraction, 0.976, multiply it by the initial, or the pure vapor pressure, 23.8 torr. And we're going to see in this case, the vapor pressure is going to drop slightly to 23.2 torr. And with the next one, it's a very similar question. That should just be delta P, where that little box is. For whatever reason, the symbol didn't transfer over. But we want to figure out, in this case, not the new vapor pressure, but just the change in that vapor pressure. So it's going to be a kind of a similar question. We'll just have a different type of answer at the end. So rather than getting the new vapor pressure and stopping there, Then we'll have to see how does that new vapor pressure compare to the original one, just so we can get that actual delta P. But again, we're looking at, oh, did I say glycerin last time? Okay. Glycerol. But we've got the same formula, C3H8O3, and then we're taking that and adding it to 500 milliliters of water at 50 degrees C. So in this case, the density of water is going to be 0.988 grams per milliliter rather than just 1. So we'll have to do a little bit more work there. The density of glycerol we still have. So it's going to be a very similar process initially. So with the glycerol, we've got 10.0 milliliters. And then we can use that density again, 1.26 grams per milliliter. We can use the molar mass, 92.0, what did I say, 92.09 grams per mole. And we'll see that 10 milliliters of glycerin is going to contain 0.137 moles. And then with the water, we can do kind of the same thing, but in this case, we've got to actually use that density, since we can't just go to oops, that should be milliliters. We can't just go straight to grams, just 1 to 1 in this case, because the density is slightly different now. So we've got 0.988 grams per milliliter. And then the molar mass, 18.02 grams per mole for water. Gives us 27.41 moles. But then at this point, kind of the same idea, that mole fraction for water is going to be the moles of water, 27.41 over 27.547, which is just going to be the total between those two components. And then just with the mole fraction, I haven't been writing in moles here just because they're ultimately going to cancel, but that's why we don't have units on the mole fraction. We've got moles on top, moles on the bottom, so those units just cancel each other out, and that's why we're just left with the value, which in this case is going to be 0.995. But then we can use Raoult's law again, so the new vapor pressure is going to be equal to that mole fraction times the original vapor pressure, which at this new temperature is much higher. So instead of the 23 number we started with last time, now we've got 92 because we've got it at a much higher temperature. We're going to have more of it moving into the gas phase because of it. But then the vapor pressure of the solution is going to be 87.9 torr. But since we're looking for delta P, we've got to do final minus initial. So we'll do 87.9 minus 92.5, and we'll see we'll get a delta P of negative 4.6 torr. So in this case, since we were looking for the delta P rather than the new vapor pressure, we just had to go one step further and just do final minus initial to actually quantify the exact change in that pressure. Okay, and then with the next one here, so we talked about the reason they salt the roads in the wintertime is just because making that solution lowers the freezing point, makes it a little safer in terms of transportation because it's less likely to freeze, or at least it's got to get down to that colder temperature in order to do so. Antifreeze works in a similar way, and we can see the formula there for ethylene glycol, which is going to be the primary component in the antifreeze. And again, this is going to be a non-volatile, non-electrolyte. So it's just going to be a covalent compound that's not going to evaporate. We want to figure out the boiling point and the freezing point of this solution if it's 25% mass, 25% by mass of the ethylene glycol in water. And with this one, I'm going to start out the calculation here, and then I'll move to the next slide to finish it up. But similar to some of the questions we saw in the concentration sort of portion of the chapter, if we've just got the percent mass of that solution, we can just pick however much of a solution we want, and then just use the percentage on that value. I'm going to use 100 grams of solution, just so we can have 25% become 25 grams, but you can pick any value you want. But if we've got 25 grams of the, I'm just going to put EG for ethylene glycol, rather than write out the whole formula or ethylene glycol itself, which means we're going to have 75 grams of H2O. And if we're trying to get the new boiling and freezing points for this solution, if we think about what the equation is going to be, I'm just going to do the generic one since the boiling point and freezing point are the same. It's just going to be dependent on what constant we actually have. We've got the freezing point or the boiling point constant times the molality times I, so we've got that Van Hoff factor. In this case, since it's a non-volatile, non-electrolyte, I is just going to be 1. K is just going to be a constant, and then I should give that to you since you don't have to memorize those. So that's going to be 0.51 for KB and 1.86. And these are going to be in degrees Celsius per molal. 1.86 rather, for the KF. So if we look at it, we've got the K value. The Van Hoff factor is just going to be 1. So what we need to do is get the molality, which means we'll have 0.075 kilograms of that solvent. And then we need the moles of the ethylene glycol, which is going to be 62.07 grams per mole based on that formula. So if we had 25 grams, we would have 0.403 moles. So then for the molal, we'll take that number of moles, divide it by the kilograms of solution, kilograms of solvent rather. And we'll see we'll have a molality of 5.37. So now looking at this equation, we've got K, we've got M, we've got I. So we can just go through and actually plug those in. So for KB, and then I'll do KF on this side. So we've got delta TB is equal to KBMI. So KB is going to be, let me say 0.51 degrees Celsius per molal. M is just going to be 5.37 molal, and then the Van Hoff factor is just going to be 1. So we'll see the boiling point is going to increase by 2.7 degrees. So the new boiling point, if we're thinking about pure water, 100 degrees Celsius. So the solution now, if it's boiling 2.7 degrees higher, it's just going to be 102.7. And then kind of the same idea with the freezing point one. It's just now we've got a different constant there. So we've got 1.86 degrees C per molal. Oops, and I'm going to run out of room here. 5.37 molal. And then with this, I'm just going to leave off the Van Hoff factor since it's just 1 multiplying by 1 is not going to change it, but just because I'm running out of room there. And we're going to see in this case the oops, and actually it'll be 9.99 degrees C. But with this one, sometimes we also just make that negative to begin with, because with the freezing point, since it's the freezing point depression, we're going to see it's going to decrease. So the new freezing point would be negative 9.99 degrees Celsius there. And then the next one, kind of the same idea, just a different quantity of these components in this solution, but we still have ethylene glycol in water. So we still got the same Kb and Kf values. We've still got the same molar masses for these ones. So we're going to see for the ethylene glycol, 1 kilogram is just 1,000 grams. So if we've got a molar mass of 62.07 grams per mole, we're going to see with the ethylene glycol, that means we're going to have 16.1 moles of this substance. And then with it, we can then take that number of moles and divide it by the kilograms of solvent to get that molality. So 400 or 4,450 is just going to be 4.45 kilograms. So we're going to see the molality in this case is going to be 3.62 molal. But then with the calculation itself, exact same as the previous one. So I'm just going to squeeze it in on the bottom here. But for TF, that means we'll have negative 1.86 degrees C per molal, 3.62 molal, and then just the 1 for the Van Hoff factor. So we're going to see we'll have a boiling point, or freezing point depression rather, of negative 6.73 degrees, and that'll just be the new boiling point, since it's going from 7 as the pure solvent down to that temperature now that we've made the solution. Actually, I'll do that, and then let's do that. And then for the boiling point, same idea. It's just we've got that different constant, so we've got 0.152. Same molality, 3.62. And then again, I'm just running out of room, so I'm going to leave off the Van Hoff factor. But we're going to see this is going to increase by 1.85 degrees C. So then with the new boiling point, we'll just see, since it's starting at 100 as the pure solvent, the new boiling point would just be 101.85 degrees C. So just remember, with the boiling point and freezing point of the solution compared to the solvent, we're going to kind of take those, when we make a solution, push both of those values to the extremes. So we're just going to separate them even more. That's why we see the boiling point increase, the freezing point decrease. So we're just going to see those values get further apart as we go from the pure solvent into the solution. And again, with the Van Hoff factor, it was just 1 for this one, just because ethylene glycol is going to be that covalent molecule. So it's just going to give us 1 particle per molecule. It's not going to dissociate into different ions like we could see with an ionic substance. But I think there's just a couple more that we'll look at. With this one, we want to think about what the expected freezing point is going to be for each of these. And with it, if we think about the freezing point, negative I, freezing point constant, times the molality. So we're given the molality of these. Kf, if we're assuming aqueous solution for all of them, Kf is going to be the same, because that constant is going to be based on the solvent rather than the solute. So what we need to focus on here is I and M. And even with I, we don't have the exact value, because remember, it's not going to be for like something like calcium chloride, where we've got 3 ions. It's not actually going to be 3 particles, just because we will have some of that reassociation occurring. But we can kind of just, for this question, treat it as such. So with this one, what I'm going to do is just kind of make a table of I and then M. And then with it, we'll just kind of have those multiplied, so we can see what the value on the right side is going to be. The larger the value from the product of those two values, just means we're going to have a larger freezing point depression. So we'll see that one's going to have a lower temperature there. And with it, I'll just do kind of different colors for each of these, just so we can kind of keep track of it. Hopefully there's enough. So with the calcium chloride, we're going to get 3 ions, so we'll have 3 particles, and then we've got 0.05 molal. So if we think about the product there, 0.15. With the sodium chloride, now we get 2 of the particles for every molecule there, but we've got a molality. Oh, this green's kind of tough to see on that color. But we've got a molality of 0.15, so we've really got 0.3 when we think about the product of those two. The hydrochloric acid is a strong acid, so we'll also get 2. But we've got a molality of 0.1 in this case, meaning that we'll just have a product of 0.2 ultimately. And then for the acetic acid, that's going to be a weak acid, so we're just going to get 1. And then we've got a molality of 0.05, so since we just have that single particle, the molality will be the same. And then kind of the same idea with the final substance there. I don't know what that substance actually is, but we've just got a slightly higher molality than we did with the acetic acid, so we're going to see 0.1 when we think about the products of those. So when we look at this again, this is kind of just the I and the M from that equation, but Kf is going to be the same for each of these substances if it's an aqueous solution. So now when we're looking at these, the larger the value, the more that we're going to have the freezing point decrease. So we're going to see, if we're thinking about 1 being the highest, and how many do we have? 5. 5 being the lowest freezing point. So I'll do FP. We can rank these based on that, and what we're going to see is sodium chloride is going to be the lowest, just because we've got the most particles times the molality. So we just get the biggest value, meaning that we're going to see the biggest change in that freezing point. And since it's going down, that means it's going to be the lowest freezing point. Then we'll have the hydrochloric acid being the next highest, calcium chloride following that, the C12H22O11, and then finally just the acetic acid as the highest one there. So with this one, it's not perfect, because again with I, not necessarily going to be exactly, and it actually won't be 3 for the calcium chloride, but we can kind of use that as just sort of a thought exercise to think about how these different substances, the number of particles, is going to affect the freezing point of that solution. Alright, and then with the next one, I think there's just 2 more. Yeah. With the next one here, the average osmotic pressure of blood is 7.7 atmospheres at 25 degrees Celsius. We want to figure out what concentration of glucose will be isotonic with blood. So remember, isotonic is just going to be essentially kind of the same. So when we think about a IV or something, if it's hypertonic or hypotonic, the solution that we're putting in that IV, then when it gets into the blood, we're either going to have water rush into the red blood cells or rush out of them. So they're either going to essentially burst if they get filled with water, or they're going to shrivel up and just essentially die if the water rushes out. So we need the solution to be isotonic so that we don't have that occur with the red blood cells. And in this case, we're focused on the glucose. So we want to remember with the osmotic pressure, we've got this equation. Pi, which represents the osmotic pressure, is I, so the Van Hoff factor times the molarity times the gas constant times that temperature in Kelvin. And then in this case, we're looking for the molarity, so we can just rearrange this. So if we divide both sides by MRT, we can just get the molarity by itself times pi over, oh, actually, it should be IRT. Oops. So when we look at this, we've already got the osmotic pressure. We've always got 7.7 atmospheres. The Van Hoff factor, since it's glucose, is just going to be 1. It's that covalent substance. R is going to be 0.08206, and that'll be liter atmosphere mole Kelvin. And then with the temperature, we've got 25 degrees C, but we just want to make sure that's in Kelvin. So we've got 298 Kelvin here. So we're going to see the molality, or molarity in this case, excuse me, is just going to be 0.31 when we go through and do all of that calculation there. And then with this one, just to kind of think about it from another example, this is the concentration of glucose that's isotonic. If we think about sodium chloride, NaCl, in that case, the only thing that would change with this one is going to be that piece. So with sodium chloride, that value would be 2. So what we would see with the sodium chloride is the isotonic would be half as much, so we'd get a 0.16 molar solution in that case. And again, that's assuming that the Van Hoff factor just is exactly whatever the number of particles is. With the sodium chloride, it would be a little bit less than 2. But just to make the example calculation just a little bit quicker and easier there, we can kind of think about sodium chloride as giving us 2 particles, so we've got a different value for that Van Hoff factor. So we're going to see the concentration itself can decrease just because we're going to be getting more of those particles per molecule. Yeah, and then with the last one here, a solution of an unknown non-volatile electrolyte was prepared by dissolving 0.25 grams of whatever that substance is in 40 grams of carbon tetrachloride. The boiling point of the resultant solution was 0.357 degrees higher than that of the pure solvent. Calculate the molar mass. So for this one, we've got to do a couple different things, and we're kind of thinking about this one in reverse. So in the past ones we've looked at, we've taken this much of whatever that substance is, dissolved it in X amount of water. What is the new boiling or freezing point? In this case, we know how much that boiling point is changed by, so we're going to work backwards to figure out what that molar mass actually is. So to do that, we're first going to figure out what the molality of that solution is going to be. Then once we have the molality, we can figure out, based on the amount of solvent we have, how many moles of that solution or of that substance we would need. And then using the actual mass we used, however many moles we would need, we can calculate the molar mass of that substance. So we've got to do a couple calculations here. And we'll go through each of them kind of just one by one. But with is this boiling point or freezing point? And then with the Kb for carbon tetrachloride is going to be 5.02 degrees Celsius per molal. But we've got this formula here, and when we look at the equation, we know the change in boiling point already, 0.357 degrees. Van Hoff factor, since it's a non-volatile electrolyte, and actually this should say non-electrolyte, I believe, because otherwise we don't have enough information. We don't know how much, like what that substance is. We don't know how many particles that's going to give us. So if I is anything but 1, we would need to know that. So we'll say non-electrolyte there, so just so we can assume it's a covalent substance. And that would also make more sense since carbon tetrachloride is going to be nonpolar. So we likely wouldn't be able to dissolve an ionic substance in that solution. So that should see non-electrolyte. But then the Kb is 5.02 degrees C per molal. So we've got 3 of those 4 pieces. We're just missing the molality here. So we can basically just divide both sides by 5.02 to get the molality by itself. And we're going to see we'll wind up with a value of 0.0711 molal. But then remember, molal is moles per kilogram. So in this case, we now know 0.0711 molal. We don't know how many moles we have, but we do know we had 0.0400 kilograms of solvent. So what we can do is determine the number of moles in that solution is going to be 0.00284 moles. Again, just cross multiplying there, 0.0711 times 0.04 just to get moles by itself. And then the final piece, now we have the mass, we have the number of moles. So the molar mass is going to be grams per mole. We can just take that 0.25. So I'll do double capital M just so that we don't confuse it with molarity. But molar mass will just be the 0.250 grams divided by the 0.00284 moles, which means we're going to have a molar mass of 88 grams per mole. And then with this, the last couple slides just about the colloids I did cover in the previous video, so this will just be the end